Alright, okay, in the previous examples we found the value at a particular point. So we used this formula here, and we were just finding what was happening at a particular value, because x0 is a number, p number, so we're only finding the function value at a particular point, which is all well and good if it's all you want. However, it'd be much more useful if we could get a function which was which for the general value of x, so we can plug any value of x we like into it and get an answer for it. And the way we do that is we take the previous one and we replace the p's with x's minus x0 over h's. So we don't have a particular proportion, we just put the generic proportion into it, bung it into this equation. If you rearrange the previous equation with that substitution, which you're not actually required to do, but if you can't sleep tonight, it'd be worth having a go, we can get this function here, where the b terms are expressed in these numbers. And this does look kind of horrific, but if you put it into a difference table, it's actually not too bad, because you'll notice that this term here is closely related to these guys. Okay, in fact, that one is exactly the same as that one. Okay, it works exactly the same, so there's just a difference thing going on. So if we're trying to find B2, we can go back to the previous two B1s. Okay, so this one is exactly the same as that one, and this one's the same, except that each number has been incremented by 1, so 1 becomes 2, 0 becomes 1, etc. So this one here is effectively that one, and this one is effectively that one. And then the x0 and the x2 are the numbers you will go right back to. So if we're trying to find this one here, then we need to use those two subtracted and trace it back to its original numbers. So this would be x0, and tracing it back here, this would be x2 for the bottom lines, which enable us to work out the values in these things reasonably easily, and then we can stick them into this function, which isn't too bad a function. So let's have a go at actually doing that with the example that we've been using. So here's the function, and we're going to be using, here it goes. So here's the generic formula, and we're going to be using this difference table here to work out what's going on. Okay, so this is going to give us a generic value for the function, so it's going to be f of x equals. Okay, so b0 is the 20, is the number which is associated with the first thing, so that's the 20, plus b1, which is the 0.16. Okay, x minus x0. Now x0 is the starting value, so that's this x0 here, it's the first x value that we've measured. Okay, and then the second term is b2, which is 0.008. How many zeros? 3 zeros, better get that right. X minus x0, we've already had is 30. X minus x1, okay, well x1 is this number in the middle here, which is 80. Plus b3, which is negative 2.67 times 10 to the minus 6. So negative 2.67 times 10 to the minus 6 times x minus x0, x minus x1, x minus x2, which is 130. Which is a polynomial, so we can bung x into this at any point we like, and we can get a value for f of x. Okay, and to actually write it a bit more sensibly, it's a cubic, because this term you're going to get x times x times x is x cubed. So if you expand all these brackets out and collect your terms, you're going to end up with a cubic, and the linear term comes out to be 17.953. The x term 0.27. The quadratic term 0.00144 x squared, and the cubic term is obviously just this thing, because it's going to be a single x cubed, so minus 0.0000267 x cubed. Okay, so you can see that the most dominant term is the constant term, and then the other terms become less and less significant as you go along. Okay, so that's a general function for our curve. And if, just a little note, if you make x equal 50, if you plug x equals 50 into that, then f of x comes out to be 22.57, and that's just worth comparing with what we did in the first video for this piece of work, because it will show you that it comes out pretty much the same. Okay, so that's how we make a general polynomial. So we now have a polynomial which works for any value of x within that first range, because this is based on the assumption that x naught is equal to 30, so only it's going to be the polynomial for this range where x naught is 30. If you want to do polynomial further down here somewhere, you'd have to use a value, x naught would change to the pivot point. Okay, so that's the function that we can use for estimating the height of the hill at any point.